Carbonyl containing groups are a very important group, which is a carbon double bonded to an oxygen, because it turns out they are very reactive. There are many functional groups that contain this carbonyl group, and we can divide those into two broad categories. The first is where your carbonyl carbon is bound to either a hydrogen or a carbon. So that would be your aldehyde and your ketone. And the other category would be where your carbonyl carbon is bound to a heteroatom. And you see here, we have a carboxylic acid, an ester, and an amide. So what we're going to see is that an ester and an amide are what we call carboxylic acid derivatives. Carboxylic acid derivatives. And this is because they can be synthesized from or made from carboxylic acids. We will talk about those reactions in a separate video. In this video, we're going to talk about the aldehyde and the ketone reactions, where we're going to look at oxidation and reduction of our aldehydes. And then we're going to look at ketones, where we're going to see that oxidation is not possible, but we will be able to reduce them. Let's recall what we mean by oxidation. Oxidation is just the increase in the number of carbon-oxygen bonds or a decrease in the number of carbon-hydrogen bonds. So here I'm showing that reaction, where again I have my aldehyde. It's an aldehyde because I have a carbonyl group, and that carbon is bound to a hydrogen. This is characteristic of an aldehyde. So when you have this group, you are able to oxidize it by adding an oxygen between your carbonyl carbon and your hydrogen. And by doing this, you have increased the number of carbon-oxygen bonds, and that's why this is considered an oxidation. So we've already actually seen this when we talked about the oxidation of primary alcohols. Recall that with a primary alcohol, the first oxidation step required that we removed a hydrogen from here and a hydrogen from there, and that allowed us to create a double bond here between the carbon and the oxygen. And that's how we were able to derive this carbonyl group with a hydrogen still attached, because we had a hydrogen remaining there. And then after we had this aldehyde, we further oxidized that aldehyde into a carboxylic acid. So in this video, we are basically just focusing on this last step here that we've already talked about when we talked about oxidation of primary alcohols. We also talked about how ketones were not able to be oxidized any further. So let's recall why this was the case. So with a ketone, what's characteristic about a ketone is your carbonyl carbon has carbons bound on either side. There is no hydrogen present attached to the carbonyl carbon. So what this means is that I am unable to further oxidize this carbonyl containing group here in this ketone. I'm unable to further oxidize it because there's no hydrogen for me to oxidize. And for this reason, we said there was no reaction when we have a ketone. All right, let's do some examples. Right. What product is formed when each compound is treated with potassium dichromate? So the first thing to recognize here is that this is an oxidizing agent. So this is going to help us oxidize our starting material. Right? Then the next thing to recognize, or the next thing we need to determine, is whether we have an aldehyde as a starting material or some sort of alcohol. Okay, so right now, this CHO type of writing here, this means this is an aldehyde. So if I were to write this in a way that you will more easily recognize it, the reason I know this is an aldehyde is because what this type of notation is telling me is that that hydrogen is bound to the carbon. And then this oxygen, to satisfy the octet rule, will need to be double bonded to that carbon. So let's go ahead and write in our CH2 group. And then that is going to be bonded to a carbon that is then bonded to an H, but then this has to be our oxygen. So that's what that means there. So once you recognize that, then you can see that we have an aldehyde, and therefore we can further oxidize this into a carboxylic acid, because this is an aldehyde. So that means I can insert an oxygen between that carbonyl carbon and the hydrogen. And I've just written this in skeletal structure so that this CH2 group here is this point up there. And then this is my carbonyl carbon double bonded to the oxygen. And this is the oxygen I've added in order to oxidize my aldehyde into a carboxylic acid. Okay. And then recall that this notation here, this bracket with an O inside, that just means I have an oxidizing agent. And in this case, it's going to be potassium dichromate. All right, let's look at our second example here. Here, I notice I have an alcohol. Well, we've learned that alcohols can be oxidized. So let's see if it is possible. First step is locate the carbon that bears your functional group. In this case, the functional group is a hydroxyl group. And in order to oxidize this, we need to have a hydrogen available on this carbon. So we find that on this carbon, we have 2 hydrogens. So this means that I would need to remove one of those hydrogens, one of these, in order to create a double bond here. And I can do so. So this means I can carry out this oxidation step. I'm going to go ahead and write my product that has 6 carbons. So 1, 2, 3, 4, 5, 6. And now at this point, I have a double bonded oxygen. I'm going to draw that pointing up. And then I still have a hydrogen remaining. So I'm going to draw that in to show that I now have an aldehyde. So because now I have an aldehyde, this means that I can oxidize this further because this hydrogen here can take up an oxygen. So I will do this, and I'll do 1, 2, 3, 4, 5, 6. I still have my double bonded oxygen. And then now I'm going to have an OH group there, and effectively turning this into a carboxylic acid. And again, recognize that the reason this is possible is because I started with a primary alcohol. Recall that a primary alcohol means that the carbon that bears the hydroxyl group, this carbon is bound to just one other carbon. Okay? That's what makes it a primary. Let's do another example. Okay. Here, they're asking for what product is formed when each compound is treated with an oxidizing agent. So we need to determine if this can be oxidized. I recognize that I have a ketone. How do I know I have a ketone? Well, first locate the carbonyl carbon, which is this one here, and then determine what is bound to it. There's a carbon and then another carbon. And this is the definition of a ketone. So what this means is that because I don't have an aldehyde, or because on this carbon, I don't have a hydrogen there to further oxidize, then that means there's going to be no reaction. So if I try to oxidize this, nothing will happen. There's no reaction. Let's look at the second example. Okay, now I locate the carbon that has the functional group. In this case, it's a hydroxyl group. And then I have to determine if this carbon has a hydrogen that I can remove from it. So this carbon right now has 1, 2, 3 bonds. That means that there must be 1 hydrogen here. So I can remove this hydrogen and that one, so that then I can create a double bond there. So this means I can, in fact, oxidize this alcohol. So it's going to be 1, 2, 3, 4, 5. And then I'm going to have a double bond O on that second carbon. And then I ask myself, can I oxidize this further? Well, in order to oxidize it further, I would need to have a hydrogen on this carbonyl carbon here. And I don't. I have a carbon on this side and a carbon on the other. So what I have made here is a ketone, and therefore it cannot be oxidized further. Okay. You make a ketone when you start out with a secondary alcohol. And that is because this alcohol, it's secondary because you have a carbon on this side and a carbon on that side. So when you remove the 1 hydrogen that it has, you necessarily end up with a ketone. Okay, so that is oxidation. Now we're going to talk reduction. Reduction is just going to be the opposite or the reverse of oxidation. Okay, so reduction is going to now be a decrease in the number of carbon-oxygen bonds rather than increasing them. We can also think about it as increasing the number of carbon-hydrogen bonds. So let's recall this reaction again, our primary alcohol being turned into an aldehyde. This was an oxidation because we increased the number of carbon-oxygen bonds as shown here. Now we're going to go from an aldehyde into an alcohol. We're doing the reverse. So this is going to be now a reduction. And that's what I'm showing here. So we can go from an aldehyde to a primary alcohol by reducing, by carrying out a reduction reaction. This is actually going to be very similar to what we've already seen with hydrogenation of alkenes, where we had a carbon double bonded to another carbon, and then we could add H2 or a hydrogen to either carbon in order to make an alkane. Okay. Now, with an aldehyde and then also with a ketone, we basically have a carbon double bonded to an oxygen. The difference is just this oxygen here and the carbon there. But this oxygen is going to be happy to take a hydrogen. So that means that we can break that bond, as we did with the hydrogenation reactions of alkenes. We're going to break one of those bonds so that we can add a hydrogen on this side and then a hydrogen on the other side. And that is basically the product that you get here. And when you start from an aldehyde, you will end up with a primary alcohol. Again, this is a primary alcohol. because the carbon that bears your hydroxyl group is bound to just one other carbon. Let's see how this works with a ketone. It's going to work the same way. It's just your product is going to be a secondary alcohol rather than a primary. But we do the same thing. We break that bond there so that we can add hydrogens on either side. And then you end up with your H2 down here. So this means that our reaction is also going to be with H2, and we're going to use our palladium catalyst as we did previously. And this is the case for both. So let's go ahead and look at an example. Okay, what alcohol is formed when each carbonyl compound is treated with H2, so this is my reactant, and the catalyst PD. Right, so first thing to do is look at your starting material and identify the functional groups. This is going to be my functional group here because it contains a heteroatom. Specifically, this is going to be an aldehyde because we already talked about that CHO means that this hydrogen is bound to the carbon, and therefore then this oxygen must be double bonded to that carbon. So this means that I have something that looks like this. I'm going to go ahead and draw it out so that it's more obvious what we're doing. Okay, so I have CH3, CH2, and then my six-membered ring with the double bonds. And then I'm going to draw my carbon, double bonded to the oxygen, and then the hydrogen, which is bound to that carbon. Okay, so I just rewrote this so that we can see it more easily. All right, now I want to break that bond just like we did with hydrogenation. I'm going to break that bond here. So one of them will go, and then I can add a hydrogen to that side and a hydrogen to the other. So let's write that with a full arrow. So here we're going to have H2 and palladium. And so I'm going to draw my six-membered ring. And then now at this carbon, I have an oxygen. I have broken that double bond because now I want to attach a hydrogen to that oxygen. And now this carbon is going to have a hydrogen that I've added, and then the hydrogen that it already had. And then on this side, I have my ethyl group. And this is a six-membered ring. Okay, so this is going to be my product. My product is basically a primary alcohol. And that's because I started from an aldehyde. All right, let's look at the next one. The next one is a ketone. Can I reduce this? Well, I can. All I have to do is break this double bond and then add a hydrogen on this side and add a hydrogen on the other. So let's go ahead and do that. H2 in the presence of palladium. And so draw your six-membered ring. Oops, let's do that again. Sorry about that. I clicked the wrong thing. All right, there we go. So let's do, so we have a methyl group there, and then I break that oxygen, and then now I have a hydrogen and another hydrogen. So actually, I'm not going to draw that hydrogen in because I'm drawing a skeletal structure, so we don't need that there. Okay, so what this means is that I have created what is a secondary alcohol because I have one going that way, one going the other. So this is a secondary alcohol. All right, lastly, H2 and PD. This here is a 2, it got cut out. Okay, so what do I have? I have a ketone. So I locate my double bond. I'm trying to reduce this. So I'm going to break one of those bonds and add an H there, another one here. So that means my final product will be this, where now I have CH3, CH2. Then I will put that hydrogen I added down here, and then I'll do this in the other side. And this is also going to be a secondary alcohol. And that is how you reduce ketones or aldehydes. Again, it's going to be pretty similar to what we did with alkenes, where we just broke that double bond and added hydrogens to the atoms on either side of that double bond.